Hey, it's video 11-1, man. Ideal gas law, molar volume, and molar mass and density. So, chapter 11, looking at molecular composition of gases. Okay, first thing we look at, another gas law. Okay, this is called the ideal gas law, the IGL. Now, this is simply PV equals nRT. So, you've seen some of these symbols before. You know, P is volume, or P is pressure, V is volume, T is temperature. Okay, N stands for moles. And this one right here, R, is known as the ideal gas constant. Okay, it is a constant. Its value can change though depending on what kind of units that you use. So, units, liters times atmospheres over moles times Kelvin. Okay, you can write it like this, liter atmosphere over mole times Kelvin. Okay, why do you get weird units like that? Well, if you solve for R, move everything on the other side, you end up with PV over NT. Okay, and you end up with a pressure unit, which is your atmospheres, a volume unit, which is your liters, and which is moles, and temperature, don't forget, must be in Kelvin. So that's why you end up with those weird units. Okay, now you know we can also express pressure in different units. So if instead of using atmospheres, you use millimeters of mercury, okay, you end up with a different value because remember, 1 atmosphere is 760 millimeters of mercury. Okay, and if you wanted to figure out where that 62.4 came from, simply just do dimensional analysis. 0.0821 liters times atmospheres over moles times Kelvin. Okay, and then all you're going to change is get rid of liters, or get rid of atmospheres rather, and change it into millimeters of mercury. Okay, all you're doing is just simple dimensional analysis, and you know 760 millimeters of mercury is 1 atmosphere. Okay, don't forget. Let's clear all this stuff so you can see it. Temperature has to be in Kelvin. Okay, now, when do you use the ideal gas law? If you have a single set of conditions. Okay, basically this is for an ideal gas or a gas that's behaving like an ideal gas. You have 1, 2, 3, 4 variables. You can pick 3 of them. Okay, and then the 4th variable has to follow this basic law. R is equal to PV over NT. You can pick 3 variables. Okay, but then the 4th one has to fall in line so that P times V over N times T will always be equal to R. Okay, now, molar volume of a gas. Don't forget the term molar volume. Molar refers to 1 mole. Okay, so what is the volume for 1 mole of gas? Okay, at STP conditions. Don't forget STP, standard temperature and pressure. Okay, what's the volume for 1 mole of a gas? In other words, what's the molar volume? Okay, take the ideal gas law, PV equals nRT, okay, and rearrange it so we get nRT over P. Solve for the volume. Okay, now standard temperature. Don't forget it has to be in Kelvin, so use 273.15, and standard pressure can be in any units as long as it's equal to 1 atmosphere. We'll make it easy and just say 1 atmosphere. Okay, so we plug those values in. R is this is a gas constant again. Okay, N by definition has to be equal to 1 mole, since we're talking about the molar volume. Okay, temperature, pressure, and you come out with the volume of 1 mole of gas is equal to 22.4 liters. Okay, now, nice thing about this, doesn't matter what the gas is. Let's go back and look at the question. So it's just asking what's the volume of 1 mole of the gas. It didn't specify what the gas was. Okay, so we can now say at STP conditions, if you have 1 mole of gas, as long as it is a gas at STP conditions, it will occupy 22.4 liters. Now going back to chapter 2, this term here, will occupy, means equals. So you have an equality. Okay, 1 mole of any gas, as long as it's at STP, is equal to 22.4 liters. Okay, so you can do inequality between moles and liters. So now you can do dimensional analysis. Okay, now molar mass and densities of a gas. Okay, molar mass, remember, the units are just simply mass over moles. Okay, or molar mass is equal to m over n. Okay, and you may want to write it like this: m over n. Now, from the ideal gas law, PV equals nRT. If we solve for n is equal to PV over RT. Okay, now let's take that and plug it back into that equation. So we get molar mass is equal to m over PV over RT. Okay, now that looks like this. Okay, now you want to simplify this. Okay, basically multiply the top and bottom by RT. And multiply the bottom by RT. Okay, all that cancels out. And you get MRT over PV. Okay, you can figure out the molar mass of a gas if you know these conditions. You know the mass of the gas, you know its temperature, pressure, and volume. Okay, plug it into the equation, that'll give you the molar mass of a gas. Okay, now density. This goes back a little ways. Density is equal to mass over volume. Okay, so from the ideal gas law, PV equals nRT. Let's solve for volume, okay, and plug that into the equation up here. Okay, substituting into the top, we end up with this. You want to see it a little better? D is equal to M over nRT over P. Okay, simplify it again, just like what we did before. Multiply the numerator and the denominator by P. That goes away, and we end up with MP over nRT. Okay, now, one more thing. Notice this right here. M over N. You saw that earlier. Molar mass is M over N. So in place of M over N, I can substitute molar mass. Okay, so that basically turns into molar mass times the pressure divided by RT. Okay, so we can say D is equal to molar mass times pressure over RT. And your review question. Which sample of gas has more particles in it? One where you have 1 mole of hydrogen at STP, or one where you have 1 mole of oxygen at 2 atmospheres and 20 degrees Celsius?